Hello and welcome to this video for Electropages. I'm your host Robin Mitchell, and today we're here at Avnet Silica in the UK, and I'm joined by my very good friend Thomas Hauer, the man who knows power. So in this video we're going to be talking about gallium nitride, GaN, and its role in the field of electronics and where it's going. Now, compared to the other technologies, let's just talk a little bit about what is GaN and why is it becoming an important technology.
GaN itself is a wide-bandgap material, and so how it's made, it has a base layer, it's silicon, then it has buffer layer, and then the GaN device is grown on top of it. GaN devices are all lateral devices, so there's no like vertical current flow, and so this gives different, say, properties and switching and so on. So in theory, a GaN device so a GaN power transistor can switch at the speed of 200 volts per nanosecond.
Oh, blimey, that's like 10 times more than that's
silicon.
That's a lot.
In practice, we will settle around like 100 volts per nanosecond, so half of it. So that gives lots of advantages when it comes to switching losses, but also challenging aspects in EMI.
Of course, because you've got such fast switching, that's going to have massive emissions across a lot of. Yeah, that does actually make sense. At high powers, big emissions, sharp drops. But in terms of the technology itself, if I remember correctly, it's originated from, would you say, from the sort of the RF field of electronics?
Yes, kind of. I mean, the first, let's say, high-ish voltage GaN devices were GaN on silicon carbide.
That's interesting. GaN on silicon carbide.
Yes, and that's down to the fact that the lattice structure matches quite good. And this was actually the research topic of University of California, I think, so 20-ish years ago. And this is where kind of the GaN interest started in the scientific community. And then they kind of moved forward, and they figured out, well, silicon carbide is maybe not the best base material because it's expensive. And then they moved on to search for different materials. I think from a lattice match point of view, I think sapphire is also quite good, but also not cheap material.
And what we're talking about there is the fact that different crystals have different structures in terms of like the arrangement of their atoms, and you want them to kind of like be similar so that they bond well.
So the thing is, you always need a buffer layer, and the better they match, the less thickness the buffer layer can have, and the less stress.
And that makes sense. So if they were almost identical, then when it comes to growing that layer, it's not going to be like it can align itself essentially to that layer, and it's going to like grow without any defects and sort of warping or stresses in the planes. Okay, that actually makes sense. That's interesting. So you have to find a material that's as close as you can get. Hence why you're saying silicon carbide did all right at the beginning, but then they found probably it's expensive anyway to try and grow it on there. So you want to try and find a more cost-effective solution.
Yes, and they found like, okay, silicon is also there, but there's also sapphire, and so they ended up with using silicon because we have lots of wafers,
of course,
and big wafers, and you also can use the old manufacturing facilities because you don't need tiny structures like...
Exactly, we've had that kind of technology for sort of 50 years, so then that wafer is going to do a perfectly fine job as long as it's smooth enough, and we've got polishing techniques that can go right down to sort of like the atomic scale anyway, so then that's what makes sense.
And then they create the buffer layer, and then they grow the GaN device.
So in some ways you could say that GaN is on top of SiC.
Yeah, sort of, yes.
No, I think this is going to be a really interesting conversation because there's this huge debate and there's this huge sort of like, I'm almost tempted to say fight going on between some engineers about which technologies reign supreme, IGBT, silicon carbide, silicon, GaN. But I think the conversations we've had has sort of revealed the truth of the nature. So just sort of for the sake of the audience, just tell us a little bit about what's really going on when comparing these technologies.
The thing is, when you kind of are in an argument about what's better for what and so on, there's no like black and white, there's always like gray scales. And for example, look at flyback topologies. Like AC to DC, we're looking like 110 volts to what, 12 volts or something. If it's about size and efficiency, then use a GaN flyback. So because you're switching fast, you have a high switching frequency, and so this is making the flyback transformer smaller, the whole device is smaller. I mean, you see this modern USB Type-C phone chargers and notebook chargers, incredibly small. That's not possible with silicon. And when it comes to, I mean, that's GaN at the moment stops at 640-ish. There is silicon devices, so silicon MOSFETs, IGBTs. There's in that same range silicon carbide, and then there's GaN in the same range. So what should I pick? And it's always down to, let's say, the topology and the end usage where I'm going. Motor drives, it will stay a playing field in the higher power range for silicon carbide IGBTs. In the lower power field, you can have a conversation about GaN, but you need to be aware lots of the motor drives work in a way that they can be overloaded.
And this comes down to the issue with the body diode in the GaN structure itself.
Overload, not. Overload is just with the size of the GaN die itself.
Oh, okay, yeah. So it's too much current going through something too small, whereas that situation was more about things like back EMF and overcurrent and stuff.
Yeah, when it comes to motor drive for industrial applications, for example, you have emission profile, you have a peak load, you have an average load, and a minimum load. And the power electronics to achieve that kind of load profile is never designed in a way to be continuously able to support the peak load. It's an overload case you're looking at. But the thing is, industrial motor drives need to have a lifetime for like, what, 10,000, 12,000 hours. And you can simulate and calculate the wear down of the module. So you are in a, let's say, controlled wear down of the module to achieve the lifetime, but not over designing the thing. For GaN, overload is not the thing you can do, really. And so you need to be aware that you need to design for peak load. And this does take the fun out of the equation, really, because it's then bigger and more expensive, and then it's like, where's the point to use that one? If you have like a few hundred watts motor drive for a fan or whatever, fine. There's no discussion there.
And so what this really is, so what we're really saying here is that when it comes to looking at these different technologies, they're all perfectly relevant. They're all going to be relevant to their own industries, their own applications. And so when you do see these kind of things where they say the future is silicon carbide, the future is GaN, the reality is that the future will have GaN, the future will have silicon carbide, but it won't be that because it's going to be every technology depending on what you're doing. And so I think if I remember correctly, GaN, it's got a high switching speed, so but it's got a lower voltage, sort of maximum voltage rating, which means that you use it in the smaller things, silicon carbide, bigger things. But as we discussed in the previous video, you don't want to use those things over long distances if you've got capacitance in your power cable, so then IGBTs come in, and so you have all these different applications where they all sort of work together. But there was something that I wanted to just pick up on very quickly. There is the overruling sort of like rule that I'm seeing around power is that the faster you can switch, the more efficient you can convert power. That seems to be the general impression I'm getting, and I take it that because of that, GaN would give you some of the best efficiencies in small wattage DC-DC converters.
I would say this statement is true within a range of frequencies, because when you look at transformers, what you're having essentially is a ferrite core and windings, and you're getting into some limits there. Maybe not necessarily with the ferrite cores, but with the windings. You have Litz wires and stuff, and then you have like this surface current effect.
I was about to say, this is like the skin effect, isn't it? So with a typical transformer, you tend to saturate the core before it can, we can't store any more energy. And then if you go beyond that, then you're saying it's the skin effect, because like you say, the higher the AC frequency, the current goes around the skin of the wire instead of the core, so you want to make the wire smaller and stuff, and so, but if you make the wire smaller, it will handle less current. And so I can see all these sort of factors sort of playing in, and so you might then find you've got losses in the fact that there's too much resistance in the core. So I can see these sort of things sort of coming together.
You always have some physical limitations for these statements, and when I look at the flyback controllers slash flyback GaN controllers we have in our line guides, mostly they end up at 240-ish kilohertz switching frequency, and I would say for the time being that's more than enough, because flyback kind of circuits that are kind of AC operated ones normally work at 170 to 140 kilohertz, somewhere there, because EMC. So I'm talking about industrial applications. Because of EMC, because the conducted EMC has kind of a slope down and then going into a straight line, and when you position yourself with the noise somewhere in the slope down, it's beneficial for you, because you kind of saving on the filter side.
Actually, that's an interesting question. I've got so when it comes to going up to, like, did you say 240 kilohertz?
Yep.
So that's an insane frequency for high power sort of switching. It's a fast speed.
We're talking flybacks here, and flybacks typically go to 100-ish watts, because otherwise the flyback grows too big, so the transformer grows too big, because when you look at the magnetizing curve of a transformer, you're just using one quadrant and not two, so it's like you just need to grow that.
But even in that situation where you've got a 240 kilohertz signal at 100 watts, now I am not an RF engineer or an EMI engineer, so this is going to be
neither.
Okay, we're going to find out. I'm going to try and ask this question because I'm really curious about something. Is it right to assume that the higher the frequency that you operate in, switching larger powers becomes more problematic because that energy is more easily dissipated in the form of EMI? In other words, if you switch at lower speeds, it doesn't, what's the word, kind of like, doesn't resonate as well. In a sense,
the parasitics have more effect on this. Yes, that's absolutely true. Yeah. And there are already products on the market that help you with that. So getting the leakage controlled better in switching and so forth, and synchronous rectifying on the secondary side, so you just spare out the diode and things. So there are developments in the market that take on that issue, yes, but getting it really right with EMI for, say, flybacks on GaN is not a straightforward action, I would say. So I've seen lots of power supplies like, we kind of did it right. We think we passed EMC, and then they come out of the EMC that's like, we're 12 dBs over the limit. Like,
Yeah, exactly. And then it's cost you a huge amount of money to test in the first place, and you think, right. And so this, and that is interesting because it comes back to a really interesting point about Avnet Silica, which is that with the experience that you guys have, engineers who are designing these GaN systems, they can come to you guys before they start designing and implementing to try and solve these problems before they even come up in the first place.
Yes, and we just try to get them as far as we can get in with the first questions, really, and just to kind of maneuver around the initial problems they might have. And it's never going to be the case that we're going to have zero problems. There always will be here and there some hiccups in the design, whatever. But we are trying to give the engineer company over the whole process.
Of course, and the access that you have to the different silicon vendors that you work with, you can always point people in the right direction. So that device may not work for you. This one's going to be good. That one might have better EMI characteristics, etc. So it's kind of like with such a new technology, there's going to be so many pains. There's going to be so many learning curves. All these different issues. You guys can step in and help those engineers integrate those new technologies, essentially speeding their time to market, helping them make sure they don't make trivial design mistakes and stuff like that. But in terms of actually implementing GaN, what would you say is the biggest challenge that you've seen engineers face?
It's mostly, I think, the packages, because when we're looking at
packages,
because most packages are quite unique, so you don't have second source, and most of the GaN device packages are BGA type ones, so really small ones, and you don't do this with your kind of bench top reflow oven whatsoever. So you need to have the prototype manufactured in the right way to really get the results out of it.
Oh wow, that's really, you can't just. So like silicon carbide, I've seen them in all kinds of packages that you could solder yourself quite easily.
Yeah, TU-247, for example. It's a no-brainer to just resolder it.
Yeah.
But do it with a what is it? QFN 2x2, 3x3.
Oh my goodness.
It's nothing you do with your soldering iron.
Well, unless you're absolutely insane and you really don't mind spending all day trying to heat that thing in your own personal reflow oven. But so does that mean that GaN devices aren't typically found in those nice TO packages or those kind of like chunkier sizes that you can play around with?
There are a few ones, but normally they're really in small packages because it makes no sense to have them integrated in larger packages because you deal them with stray inductance and all this kind of things you don't want to have or want to see, because when it comes to this high frequencies and you have a little bit of stray inductance, the ringing is just like killing your device.
Oh, so the size of these packages and the challenges they face in big ones, it comes down to frequency due to the fact that they operate at much higher. So with silicon carbide, even though it's still higher than sort of IGBTs and stuff, it's still low enough that it would a big sort of TO92 package or whatever we want to call it, that would still be okay to use with that technology, but GaN just simply can't do it due to that. That's really interesting. So I take it you must have issues with like routing and tracing as well in the PCB.
Yes, it also gets very tricky because when you look at 100 volts per nanosecond and then all the delays that these devices have and not have and how close it is, I once did the comparison of PCI bus routing.
I was about to say, I can imagine it must really be like, because DDR, PCI, those things are horrendous to route. You've got to make sure every single trace has the correct impedance. It's going to have the correct sort of trace length as well, and then you're matching it all together, and then signals might arrive at different times. And so it really can be a problem like that with GaN.
When you go really into the high-end design and power stuff, it might be an issue, but if you're able to place really everything very close and take care about the stuff, it's fine. Yeah. And when you look at packages, for example, to name one, it's the CC pack from Nexperia. It's quite a chunky package for SMD, and they do it for silicon MOSFETs, for IGBTs, and also for GaN. And with GaN, they have their cascode device, so 640 volts, and they use copper clip bonding to bring the stray inductance really down. To not have wire bonding, so they use, with that technology, they use copper clip bonding to bring the stray inductance down to being able to cope with the switching speeds and not bring the customer into trouble.
Copper clipping, sorry, what was it called?
Copper clip and wire bonding. There's the two technologies.
Yeah, so wire bonding, you've got your gold wire, you push down to the pad and you come down.
And then you go to the pin, next one to the pin, and when it comes to power, it's like multiple wires going to the pin. And with copper clip, it's literally a copper clip that is sintered on the
directly bond onto a lead frame almost.
It's quite common in silicon transistors. So like most of the low voltage silicon transistors from OnTime, I have it. Nexperia has it. I think ST has it as well. And for GaN, Nexperia does it as well. For silicon carbide, it's a different ballgame because the material is harder and it's more brittle. So if you just bluntly press it on silicon carbide, it might break. So it's more complicated.
And so that's where your wire bonding comes in, where it can sort of like ultrasonically weld it to that pad, and it makes more sense. But that's really interesting. So like I say, the inductance is such an issue that you can't even use a typical wire bond, which you would use in your in your sort of typical high-speed logic system. So you really have to sort of like minimize. I'm actually quite sort of quite impressed by that. The fact that you have to really. Even the packaging is a problem in a device like that. So forget the gate driving, forget the implementation. Just trying to put the thing in a package in itself is a challenge.
Yes, and you mostly lose that flip chip technology to really being able to...
Try and minimize every sort of boundary between that GaN device and whatever it is you're trying to power. So in the previous video we talked about, for example, like I think, did we say that silicon carbide had issues with long power cables due to the capacitance?
So either the silicon carbide transistors have an issue with the long cable, or the long cable has an issue with silicon carbide. So
it's got an issue with both of them. Is that the same with GaN though?
Yes.
And so again, if you've got a long length of power cable, it's better to probably use a different technology because of the fact of that.
And I mean, the newer GaN devices do have short circuit protection issues, so they switch off. but that's nothing you can work with in a continuous operation.
Right, now this is just, something's just come to my mind here. In the last video we talked about the body diode not being present in the GaN device. Is that something to do with the fact that it's built up on a buffer layer?
So I'm not a semiconductor physicist. As far as I understood, yes.
And you got that isolation between the base material, so you can't. So all of that current would basically go through the actual transistor itself. So again, this is one of those things where I think engineers watching this video could definitely take one lesson from, which is that if you've got a GaN diode, I take it you put you put your own diode in to protect it. And if I remember correctly, you said it had to be a super fast specifically.
Yes, absolutely. The thing is with GaN, it's so fast, and when you use, for example, a asynchronous boost topology with a GaN, you need to investigate quite carefully on the boost diode itself, because you're switching super fast, and if the diode on the top has imposes a huge capacitance on the switch, it's always a short circuit, and it really, really stresses the part itself.
And it's because of that high switching frequency with such a high
slew rate.
The high slew rate, which is giving you a massive voltage change in a very short time, which results in a huge current change, which is a lot of pressure to put on a tiny part. And so it just feels like to me that the nature of the problems of power really, you said it's more. You said there's just more problems, but for me, it really does feel like the nature of power problems is changing. It's like a very different environment. Before we were worried about magnetic sizes, efficiencies, heating. Now it seems to be more of an issue with like frequency, EMI, the ability to respond to these changes as fast as they occur.
Yeah, I mean, if you look in the past, we had IGBTs, silicon MOSFETs. The world was quite black and white. Now we have silicon carbide, now we have GaN. So we added more colors to the spectrum, and it's on one hand more complicated, but on the other hand, from the engineering perspective, really interesting, because what can I do to make this work with that technology, and what I'm able to do with it? And that's what I'm always trying to tell customer engineers. Like, when you start with GaN and you come from a silicon transistor design, make sure you have a kind of a proof of concept project or pre-project where you don't have necessarily a hard deadline.
Yeah.
Because then you learn the most. You build something, you break it, you build it again with some improvements, you try to break it again, maybe it breaks itself. So just learn the technology and take your time. Not aim first time right, but aim for first time learning. So
and so to me, the impression I get from that is essentially companies need to invest not just in R&D and development of new technologies, but to learn and educate themselves. It's the learning process.
It's just getting back to the kind of, I wouldn't say getting back to the school times, but
university evaluation board times.
Yes, kind of. just being curious again and try out things. And I think that's where the best things happen. Just to like, okay, what if I do this, and then just go from there.
And I think it'd be also fair to say that due to the complexity and the challenges not just the challenges, but the fact that the challenges that these devices bring are so different to the ones that you'd face with typical silicon and insulated gate bipolar transistors. It's important that if you want to use those technologies in your product line, you should already plan, almost like you say, you should almost plan little projects on the side that you can practice with, get used to using those devices, recognize the issues before you actually commit, so that when you finally are ready to use these technologies, you're like, well, I know everything to it, and so therefore use this, use that, and that's fine. But even then, in that situation, engineers who are looking for GaN devices should still come to you guys and ask, here's what I'm doing, here's what I plan to use for it, what would you recommend and what should I watch out for?
Yes, please. So the engineers can come to us in every kind of stage of their development with GaN. I had customers coming to me after they had a pre-project and said, well, actually it was rubbish, it was failing and this and that, and was asking, what were you using and how did you use it? And they would come up with kind of what they were using and how, and it was like, I could have told you that one before. And then we elaborated how we can go forward on that one. And that's a learning curve. So they learned how it's not working, but actually did not learn how it works.
Exactly. Really. By learning how it doesn't work, you've learned something. Yeah. Because the next time you do it, you won't do it that way. Yeah. And I think that's something we mentioned actually in the conversation before, which was that when engineers post all their successes, that's all fine and dandy, but we want to see where you fail as well, because that will arguably has more value, so that next time I want to use a GaN device, I'll say, well, I know he got it working, but he did the same or something similar and it had a serious situation, so I want to avoid that at all costs. So, and I think again, the general attitude I've seen in these large events is that everyone's either silicon carbide's the future or GaN's the future, but in reality, really none of them are, because they all are and they all aren't. It's every technology is going to be the same, and like you said, we've seen investment in IGBTs, we've seen investments in silicon carbide, we've seen investments probably even in standard silicon devices themselves. So just because these technologies are older doesn't mean that they're not relevant. So coming into the next 10 years, when these technologies become more prevalent, what do you see as being probably the most important industry for GaN?
At the moment, it's consumer.
And that's due to the low voltage, low power, low voltage, but higher
also
efficiency.
EMC standards, they're not as strict as with industrial. What we're not having much at the moment is automotive GaN. So I see suppliers releasing step-by-step automotive GaN devices, and I really can see it working there. And also D-class audio applications are kind of good for GaN.
I was literally about to say, it sounds like what might be more suitable for things like EV is that you'd have a silicon carbide, like you said, for the back motor, your IGBT for the front motor, but then maybe the entertainment system might be a GaN because it's a lower voltage, but you want that efficiency so that you don't drain the battery too quickly.
Exactly. I don't see GaN at the traction inverter in the cars, in the main traction inverter. It's just too power hungry. But for the displays, which are many in cars, for the climate control system, for example, for the audio system, for the secondary side of the kind of power supply for the entertainment, there's plenty of applications there. For the industrial side, maybe for some applications in power supplies, like thin rail power supplies and so forth. But what's blocking point there is a little bit the EMC regulations there, because EMC regulations are much stricter there.
And because of the fact that GaN has such high switching speeds and high voltage transients, in terms of the slew rate, it's just going to be too difficult to integrate.
I mean, there is for sure a way, but it will take longer because there are more circles. There is a way to integrate it, but it's not, I would say, that easy. Like with
well, if you're a manufacturer of industrial equipment and you've got a choice between a typical silicon device or a GaN device, even if the GaN device makes your power supply half the size, size and weight constraints aren't really a big thing in the industrial environment, and you kind of want to get out of there quicker. And in terms of complying with EMC rules, it's easier to use an older technology. So I can actually understand why people are quite hesitant to sort of jump onto it. But I think an analogy for silicon carbide and GaN is that silicon carbide is kind of going to be like the power station, but the GaN's going to be your substation, which is taking the higher voltages, bringing them down, or using them in the sort of home era. If that analogy fits a vehicle kind of thing, So
it does fit quite well, and it does distribute, let's say, the application space quite evenly, because there's a place for your IGBTs, there's SiC, and there's silicon MOSFETs, there's GaN. So I don't think there's actually the need for an argument. This is that. Just go to the application, try to solve it as most efficient as possible, and you end up with one technology that fits. Done.
And essentially just choose the right technology for your application, which sounds like to me that Avnet Silica definitely needs to get something published on that, silicon versus GaN or something, or silicon carbide versus GaN, and in that way engineers could read it and then ask you more questions.
Yes, it's going to be a longish article.
A very, very long one, because there are so many applications, these different things. So obviously you said consumer is going to be one area where GaN's going to sort of find its way in. Do you think it could also potentially find its way into sort of mobile applications, maybe also things like aerospace? With especially on the conversation of power distribution across a craft.
Difficult to say, because you have it always depends on which part of kind of aerospace stuff.
So let's say like a commercial airliners, let's say, for example.
I could imagine for auxiliary power supplies, because there's nothing really. I mean, if LED spot for reading does not go on because it's damaged, I mean, inconvenient, but it's not the end of the world.
Of course.
For flight safety stuff, silicon carbide has advantages there.
It's got that redundancy, resilience. It's probably more hardened, I'd say, so it can resist transients better, and it's not going to pop essentially as easily. And so I suspect that is it possible to put GaN devices in parallel for redundancy purposes? Because I know you can do it with silicon carbide.
If you go into the literature, it always says, in theory, yes, or basically yes. And
in theory, yes, but
I'm always a bit cautious about this. We have customers doing that, but it's not an easy exercise. When you look at 100 volts per nanosecond, and you have, for example, a flyback or something,
you've got to get the timings of those two absolutely perfect. Because if this one's fully conducting and he's not in that zone, all of it's going down there.
Yes, and if you look at the parts with the GaN power switch with integrated gate driver, and you look at the jitters of the gate driver, what they have, like it could actually be the case that one is switched on and the other one is just thinking about switching on. So, but I would not worry too much about this topic. At the moment, the GaN devices are 3, 4, 5, 6-ish amps. Suppliers are all working on higher current versions of the GaN switches, so I don't think this will be a topic of the future that people should worry, because higher current GaN devices are coming, and it's just a matter of when.
And again, like you say, it's most likely to be the sort of consumer low wattage compared to silicon carbide. So again, these issues are kind of mute, because they'll give you the efficiency, but in terms of, you're not going to need multiple devices in parallel, because you're not going to use it like that. Because once you get to that point, go silicon carbide or IGBT basically.
But one application for higher current GaNs is actually bidirectional switching, because with GaN, with the missing body diode, you can kind of easier make a bidirectional switch.
That's true, because you don't have that issue where it might reverse bias across the body.
We have 2 suppliers. One already released the part, the other one is close to release. So that's the one that released the parts already. It's like in the 40-ish volts area. So it's like 24 volt bus switching stuff on and off. So and it's just like you have one gate and one device, and you're done.
One device, and it'll go both ways.
One device, and it's blocking in both directions if it's switched off. It's a bidirectional switch.
Oh, so a GaN transistor is actually bidirectional, as in like
this configuration. So it's not like one device; it's on the chip.
Oh, there'll be lots of things around it, but it's like one. Oh, I get it. One package, and then it'll go both ways. That's really cool. That okay. So again, if the engineers who are watching this video, if they want to get involved with Avnet Silica solutions and then how they can essentially come to you guys for advice and designing and sourcing, what would you recommend that they do?
Contact us over the website, LinkedIn, whatever. Maybe they know already a salesperson or an FAE. Just get in contact, and we try to help them.
Fantastic. Well, thank you ever so much for taking the time to say this.